Everything in the universe is spinning. Not some things, not most things, everything. The planet beneath your feet is spinning at roughly 1,670 kilometers per hour at the equator. The solar system is orbiting the center of the Milky Way at approximately 828,000 kilometers per hour. The Milky Way itself is rotating, its outer stars completing one revolution every 200 million years. Galaxy clusters spin. Superclusters show rotational tendencies. Even the observable universe itself may be slowly rotating. Spin is everywhere, at every scale, in every structure. And here is what nobody tells you. We don't fully know why. Not in the deep sense, not in the sense that explains where spin came from in the first place, not in the sense that tells us why the universe chose rotation over stillness as its default state. The answer, when you follow the physics all the way down, touches on the Big Bang, on quantum mechanics, on the conservation laws that govern every particle in existence, on the formation of galaxies and solar systems and planets, on the nature of angular momentum itself. And it reveals something extraordinary. Spin is not just something things do. Spin may be one of the most fundamental properties of reality, woven into the fabric of the universe from the very first moments of existence. And the deeper you look, the further down you trace the origin of rotation, the stranger and more impossible the answer becomes. Let us start close. The Earth rotates once every 23 hours, 56 minutes, and 4 seconds. This is called a sidereal day, the time it takes Earth to complete one full rotation relative to the distant stars. The reason your day is 24 hours, rather than 23 hours and 56 minutes, is that Earth is also moving around the Sun. It takes those extra 4 minutes for the Sun to return to the same apparent position in the sky after each rotation. The Earth spins at approximately 1,670 kilometers per hour at the equator. This is fast, far faster than any aircraft, and yet you do not feel it. Because you are spinning with the Earth, because you have always been spinning with the Earth, because the spin has been constant, or nearly so, for your entire life. But where did the spin come from? The Earth formed approximately 4.6 billion years ago from a cloud of gas and dust orbiting the young Sun. This cloud, called the solar nebula, was itself slowly rotating. As the cloud collapsed under gravity, it spun faster, the same way a figure skater spins faster when they pull their arms in. This is the conservation of angular momentum, one of the most fundamental laws in all of physics. Angular momentum, the product of an object's mass, velocity, and distance from the axis of rotation, is conserved in a closed system. It cannot be created or destroyed. As the solar nebula collapsed, as the gas and dust fell inward under gravity, the distance from the rotation axis decreased. To conserve angular momentum, the rotation speed had to increase. The slow, gentle rotation of a vast cloud of gas became the rapid spin of a compact planetary system. This is why the Earth spins. This is why all the planets spin. This is why the Sun rotates. Conservation of angular momentum applied to the collapse of the solar nebula. But this answer, satisfying as it is, immediately raises a deeper question. Where did the solar nebula get its rotation? Where did the angular momentum come from in the first place? If this blows your mind, hit like. Angular momentum is one of the most fundamental conserved quantities in physics. In any isolated system, any system not subject to external torques, the total angular momentum never changes. It cannot increase. It cannot decrease. It can be redistributed among the components of the system, but the total is fixed. This conservation law is not an empirical observation, a pattern noticed through repeated experiment. It is a mathematical theorem. It follows directly from a deep principle called Noether's theorem, developed by the mathematician Emmy Noether in 1915. Noether's theorem states that every continuous symmetry of the laws of physics corresponds to a conserved quantity. The symmetry corresponding to angular momentum conservation is rotational symmetry. The fact that the laws of physics look the same in every direction, that there is no preferred axis, no special direction in space, means that angular momentum must be conserved. If the laws of physics are the same whether you are facing north or south or east or west, and they are, then angular momentum cannot change. This is not just a fact about spinning objects. It is a fact about the structure of space itself, and it has a profound implication for the spinning universe. If angular momentum is conserved, if it cannot be created or destroyed, then the total angular momentum of the universe has always been what it is now. The spin in the universe today is the same spin that was in the universe at the Big Bang, which means the angular momentum of every spinning galaxy, every orbiting planet, every rotating star, all of it traces back to the first moments of the universe. The universe was spinning from the very beginning. Or was it? Here is where the story becomes genuinely strange. The Big Bang, as our best models describe it, produced a universe that was, on the largest scales, extraordinarily uniform. The cosmic microwave background, the ancient light released 380,000 years after the Big Bang, shows us a universe that was smooth to 1 part in 100,000. Almost perfectly isotropic, the same in every direction, and a perfectly isotropic universe has no preferred rotation axis, no net angular momentum. A universe that looks identical in every direction cannot be spinning overall, because spinning requires an axis, and an axis breaks the isotropy. So the total angular momentum of the universe, if it is truly isotropic on the largest scales, is 0. But the universe is full of spinning things. How can the total angular momentum be 0 when everything is spinning? The answer is both simple and profound. The spins cancel. For every galaxy spinning clockwise, there is, on average, another galaxy spinning counterclockwise. For every planet orbiting in one direction, there is, somewhere, orbital motion in the other direction. The total angular momentum of the universe sums to 0, not because nothing spins, but because everything spins, and the spins are distributed in all directions. This is called statistical isotropy. The universe has no net rotation. But locally, at the scale of solar systems and galaxies, angular momentum is enormously important. And the angular momentum of local structures, the spin of our solar system, the rotation of our galaxy, came not from the Big Bang directly, but from a process that happened afterward. The collapse of density fluctuations into structures. For most of human history, the spin was invisible. Not because ancient peoples were unobservant. They were extraordinarily careful observers of the sky. They tracked the movements of stars and planets with remarkable precision. They built observatories, Stonehenge, the Antikythera mechanism, the great astronomical towers of Mesoamerica, to measure and predict celestial motions. But what they saw was not the Earth spinning. What they saw was the sky moving, the sun rising in the east and setting in the west. the stars wheeling overhead through the night, the moon tracing its monthly arc, the planets wandering against the background of fixed stars. The obvious interpretation, the one that feels intuitively correct, is that the sky moves and the Earth stands still. And for millennia that was the consensus. The geocentric universe, Earth at the center, everything else revolving around it. Aristotle, Ptolemy, the great tradition of ancient astronomy. All built on the assumption that the Earth was motionless. Aristotle had an argument for this. He said that if the Earth was spinning, we would feel it. A spinning Earth would produce winds. Objects dropped from a height would land behind their starting point as the Earth rotated beneath them. Birds in flight would be swept backward as the ground moved under them. None of this happened. Therefore, the Earth was not spinning. The argument was logical. It was wrong. It was wrong because Aristotle did not understand inertia. He did not understand that objects in motion tend to stay in motion, that the air, the birds, the falling objects, all of them share the Earth's rotation. All of them are already moving with the spinning Earth, and so none of them are left behind when it spins. It took until the 17th century, until Galileo and Newton, for inertia to be properly understood, for the realization to sink in that the absence of felt motion is not evidence of actual stillness. Copernicus proposed the heliocentric model in 1543, the Earth orbiting the Sun, the Earth spinning on its axis. Both ideas were revolutionary. Both were resisted fiercely, not just for theological reasons, but because they seemed to violate common sense. If the Earth is spinning, Copernicus's critics argued, why don't we fly off? Why doesn't everything fall off the surface? The answer, gravity, was not properly understood until Newton. But the clinching evidence for Earth's rotation came from an unlikely source. A pendulum. In 1851, the French physicist Léon Foucault suspended a massive pendulum from the dome of the Pantheon in Paris. The pendulum swung back and forth, and as it swung over hours, the plane of its swing slowly rotated. Not because anything was pushing it. The pendulum swings in a fixed plane relative to the stars. It is the Earth and the Pantheon that rotates beneath it. Foucault's pendulum made the Earth's rotation visible for the first time, a direct, undeniable physical demonstration that the ground beneath your feet is moving. The crowd that watched the first demonstration was reportedly speechless. For the first time in human history, the spin of the Earth was not an inference or a theory. It was something you could see with your own eyes, in the slow, relentless rotation of a pendulum's swing, the invisible made visible, the spin of the world finally acknowledged. After the Big Bang, the universe was not perfectly smooth. The cosmic microwave background shows us tiny density fluctuations, regions slightly denser than average, regions slightly less dense. These fluctuations, seeded by quantum mechanics during inflation, are the seeds of all structure in the universe. As the universe expanded and cooled, these density fluctuations grew under gravity. Dense regions attracted more matter. They began to collapse. And as they collapsed, something interesting happened. They were not perfectly spherical. The density fluctuations were irregular, lumpy, asymmetric. And as a collapsing region of matter fell inward, the gravitational pull from neighboring density fluctuations, neighboring lumps of matter, was not perfectly symmetric. Different parts of the collapsing region felt different gravitational pulls from different directions. This asymmetric gravitational influence, called a tidal force, applied a torque to the collapsing region. A torque is a twisting force, the kind that makes things rotate. And under the influence of these tidal torques from neighboring density fluctuations, the collapsing cloud of gas and dark matter began to rotate. This process, called tidal torque theory, is the leading explanation for why galaxies spin, why the Milky Way rotates, why spiral galaxies have the beautiful, sweeping arms that are the signature of rotation. Before collapse, the proto-galaxy had no net angular momentum, or very little. But as it collapsed, tidal torques from neighboring structures applied a rotational twist. Angular momentum was transferred from the large-scale structure of the cosmic web into the forming galaxy. The galaxy collapsed and spun up, just as the solar nebula spun up as it collapsed to form our solar system. The pattern repeats at every scale. Large structure collapses. Conservation of angular momentum spins it up. Tidal torques from neighbors add rotational twists. The result is a spinning galaxy. And within that galaxy, the same process repeats for individual stellar nebulae, collapsing to form spinning solar systems. And within those solar systems, the same process repeats for individual planets, accumulating spin from the asymmetric accretion of material. Spin cascades down through the scales, from the largest structures in the universe to the smallest worlds. Everything spinning for the same fundamental reason. Collapse plus conservation plus asymmetry equals rotation. We have traced the spin of planets and galaxies to the conservation of angular momentum and the asymmetric collapse of density fluctuations. But there is another kind of spin in the universe, a spin that is not the result of anything rotating, a spin that is intrinsic, built into the fundamental particles of matter themselves. Quantum spin. Electrons have spin. Protons have spin. Quarks have spin. Photons have spin. Every fundamental particle in the standard model of physics has a property called spin, a quantum number that behaves mathematically like angular momentum. But quantum spin is not classical rotation. An electron does not spin the way the Earth spins, rotating about an axis, with different parts of the electron moving at different speeds. The electron is, as far as we can tell, a point particle. It has no spatial extent to rotate, and yet it has spin, intrinsic angular momentum, with a specific, fixed value. Spin half for electrons, quarks, and protons, spin 1 for photons and the carriers of the weak force, spin 2 for the hypothetical graviton. These values are fixed. They cannot be changed. An electron is always spin half. It cannot be made into a spin 0 or spin 1 particle. Quantum spin is not acquired through rotation. It is a fundamental property of the particle, as fundamental as its mass or its electric charge, and it has profound consequences. The Pauli exclusion principle, the rule that no two identical fermions can occupy the same quantum state simultaneously, follows directly from the half-integer spin of electrons and other fermions. This principle is why atoms have the structure they do, why the periodic table has the form it does, why matter is solid and does not collapse into itself. The stability of matter, the fact that you can sit on a chair without falling through it, is a consequence of quantum spin. Spin is not just a property of rotating objects. At the quantum level, spin is what makes matter matter. The spin of the Earth does not just affect the length of the day. It shapes everything that moves on the planet's surface. As the Earth rotates, any object moving across its surface, air, water, a projectile, experiences what appears to be a deflecting force. In the northern hemisphere, moving objects are deflected to the right. In the southern hemisphere, to the left. This is called the Coriolis effect, named after the French physicist Gaspard Gustave de Coriolis, who described it mathematically in 1835. The Coriolis effect is not a real force in the sense of a push or pull. It is an apparent force, an effect that arises from observing motion in a rotating reference frame. From the perspective of someone outside the Earth, looking down from space, there is no Coriolis force. Objects simply move in straight lines while the Earth rotates beneath them. But from the perspective of someone standing on the rotating Earth, objects appear to be deflected. And the consequences are enormous. Hurricanes and typhoons rotate because of the Coriolis effect. The Earth's rotation gives a slight rotational bias to large pressure systems, counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. Ocean currents are shaped by the Coriolis effect. The great gyres, the circular patterns of ocean circulation that redistribute heat around the planet and drive weather patterns, exist because of the Earth's rotation. Long-range artillery shells must be corrected for the Coriolis effect. A shell fired over a long distance in the northern hemisphere will land slightly to the right of where a non-rotating Earth calculation would predict. Artillery tables have accounted for this since the 19th century. Even rivers are slightly affected. In the northern hemisphere, rivers tend to erode their right banks slightly more than their left, because the Coriolis effect deflects flowing water to the right. The spin of the Earth, a consequence of the conservation of angular momentum dating back to the formation of the solar system, shapes the weather, the oceans, the rivers, and the landscapes of every continent. Spin is not just a property of the Earth, it is a force that acts on everything the Earth contains. The Sun rotates, not uniformly, which is itself one of the strangest things about it, because the Sun is not a solid body like the Earth. It is a plasma, a superheated gas of ionized particles, and different parts of the Sun rotate at different speeds. The equator of the Sun completes one rotation approximately every 25 days. The poles take approximately 35 days. The mid-latitudes fall somewhere in between. This phenomenon, called differential rotation, has profound and far-reaching consequences, because the Sun carries a magnetic field. And as different latitudes rotate at different speeds, the magnetic field lines, initially running roughly from pole to pole, are stretched and twisted and wrapped around the Sun. They are pulled into tighter and tighter configurations as the equator races ahead of the poles. Over time, the magnetic field becomes extraordinarily tangled, knotted. The field lines bunch together in regions of intense magnetic concentration. These concentrations inhibit the convection of heat from the solar interior. They cool the surface locally, and they appear as dark patches, sunspots, visible on the face of the Sun. Sunspots have been observed for thousands of years. Chinese astronomers recorded them in 28 BCE. Galileo studied them in the early 17th century and used their movement to determine the Sun's rotation rate. But sunspots are not merely dark patches. They are the surface signature of an extraordinarily powerful and complex magnetic system, the solar dynamo. The solar dynamo, driven by the differential rotation and the convective motion of plasma within the Sun, generates and maintains the Sun's magnetic field. It drives an 11-year cycle of solar activity, the solar cycle, in which the number of sunspots rises and falls, the magnetic field periodically flips its polarity, and the Sun's activity level varies between solar minimum and solar maximum. At solar maximum, when the magnetic field is most tangled and active, the Sun produces more solar flares and coronal mass ejections, enormous eruptions of plasma and magnetic field that hurl billions of tons of charged particles into space at millions of kilometers per hour. When these eruptions strike Earth, when the solar wind carries the energetic particles of a coronal mass ejection toward our planet, they interact with Earth's own magnetic field. They produce the auroras, the northern and southern lights, as charged particles spiral along magnetic field lines and excite atmospheric molecules into glowing curtains of green and red and violet light. The auroras are spin talking to spin. The Sun's differential rotation, twisting its magnetic field into knots, producing eruptions, launching plasma across interplanetary space, striking Earth's magnetic field, which is itself generated by the rotating liquid iron core of our spinning planet. Spin upon spin upon spin, all the way from the solar interior to the shimmering lights in the polar sky. And the solar cycle, the 11-year rhythm of solar activity driven by the Sun's rotation, affects Earth's climate, affects satellite operations, affects radio communications, affects the aurora visibility that has inspired human wonder since before recorded history. The spin of the Sun is not an astronomical curiosity. It is one of the most important forces shaping life on Earth. We discussed pulsars in our neutron star video, but in the context of spin, in the context of why everything rotates, they deserve a specific focus. Pulsars are rotating neutron stars, dead stellar cores compressed to the size of a city, spinning with extraordinary speed. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second. 716 complete rotations every second. How did a dead star come to spin this fast? The same process that spins everything else. Conservation of angular momentum. When a massive star dies in a supernova, its core collapses. A core that was perhaps 1,000 kilometers across collapses in less than a second to a neutron star roughly 20 kilometers across. The radius decreases by a factor of 50. Conservation of angular momentum demands that if the radius decreases by a factor of 50, the rotation speed must increase by a factor of 50 squared, 2,500. A stellar core rotating once every few hours becomes a neutron star rotating dozens of times per second. In millisecond pulsars, the fastest spinners, the neutron star has been further accelerated by accreting material from a companion star. The falling matter carries angular momentum. It spins the neutron star up further, to hundreds of rotations per second, 716 rotations per second. The surface of PSRJ 1748-2446 AD is moving at approximately 24% of the speed of light. A dead star, spinning at a quarter of the speed of light, because of the conservation of angular momentum. The same law that makes figure skaters spin faster when they pull their arms in, applied to the collapse of a stellar core, producing the fastest rotating solid objects in the observable universe. Spin at its most extreme. Spin has a property that seems almost magical the first time you encounter it. It resists change. A spinning object, a gyroscope, a spinning top, a rotating planet, resists any attempt to alter the direction of its rotation axis. The faster it spins, the more strongly it resists. The more massive it is, the more powerfully it fights back against any force that tries to tip it over or redirect it. This property is called gyroscopic stability, and it follows directly from the conservation of angular momentum. To change the direction of a spinning object's rotation axis, you need to apply a torque, a twisting force. The angular momentum vector must be redirected. And because angular momentum is conserved, changing its direction requires a continuous application of force. Without that force, the axis stays pointing where it is. The spinning top does not fall over, not while it is spinning fast enough, because any gravitational torque that tries to tip it causes the top to precess instead, to slowly rotate its axis in a circle rather than tipping. This precession is itself a consequence of angular momentum conservation. The torque changes the direction of the angular momentum vector, but instead of tipping the top, it causes the vector to sweep in a circle. Gyroscopic stability is not just a physics curiosity. It is one of the most important phenomena in engineering, in navigation, in the functioning of the modern world. Gyroscopes, spinning masses mounted so they can rotate freely, maintain their orientation regardless of how the platform around them moves. They point in the same direction in space, stubbornly, precisely, no matter how the ship or aircraft or spacecraft carrying them turns or pitches or rolls. This makes them extraordinarily useful for navigation. Before GPS, before satellite navigation, the gyroscope was the primary tool for inertial navigation. Ships crossing the open ocean, aircraft flying through clouds, submarines navigating beneath the polar ice cap, all relied on gyroscopes to know which direction they were heading and how their orientation was changing. The gyroscope does not need to see the stars, does not need radio signals, does not need any external reference. It simply spins, and by spinning, it remembers where it was pointing when it was set in motion. It carries its orientation through time. Modern aircraft carry multiple gyroscopes as backups. Spacecraft use gyroscopic reaction wheels to control their orientation, spinning masses that can be sped up or slowed down to rotate the spacecraft without using rocket fuel. The Hubble Space Telescope maintains its extraordinarily precise pointing, stable enough to track a moving coin from a distance of several hundred kilometers, using gyroscopic control. Even the Earth itself acts as a gyroscope. Its spinning axis, tilted at 23.5 degrees to the plane of its orbit, maintains that tilt with extraordinary stability. Not perfectly. The gravitational pull of the Moon and the Sun causes the Earth's axis to precess slowly, completing one cycle in approximately 26,000 years. This precession changes which star is the North Star over millennia. 12,000 years ago, the North Star was Vega. In another 12,000 years, it will be Vega again. But the tilt itself, 23.5 degrees, is maintained by the gyroscopic stability of the spinning Earth. And that tilt is what gives Earth its seasons, what creates the dramatic temperature differences between summer and winter, what makes the tropics warm and the poles cold. The seasons, the rhythm that has shaped agriculture, civilization, and the entire history of human life on Earth, are a consequence of gyroscopic stability, of angular momentum conservation, of spin. The universe does not just spin, it uses spin to remember, to stabilize, to maintain the structures that make complexity and life possible. Spin is not chaos. Spin is order. the most fundamental, the most conserved, the most persistent form of order in the universe. If pulsars are the most extreme conventional spinners, rotating black holes take spin to its absolute limit. In our black hole video, we discussed the Schwarzschild black hole, the non-rotating solution to Einstein's field equations. But most black holes in nature are not non-rotating. They spin. A rotating black hole is described by the Kerr metric, a solution to Einstein's equations derived by mathematician Roy Kerr in 1963. And the rotating black hole is far stranger than its non-rotating counterpart. A rotating black hole does something that a non-rotating black hole cannot do. It drags space-time with it, not metaphorically, not approximately, literally. The rotating mass of a black hole, the spinning singularity at its center, twists the fabric of space-time around it. Space-time itself is dragged in the direction of the rotation. This effect is called frame dragging, or gravitomagnetic effect, or the Lenz-Thirring effect, after the physicists who first described it. Near a rapidly rotating black hole, it is physically impossible to remain stationary. Even if you fired your rockets at maximum thrust, pushing with all the force you could generate, the dragging of space-time itself would carry you around the rotating black hole. You would be orbiting, not because gravity was pulling you into orbit, but because the spinning black hole has twisted the geometry of space so severely that forward is no longer a direction you can choose. You are carried along with the rotation of space-time itself. The region where this dragging becomes irresistible is called the ergosphere. It surrounds the event horizon of a rotating black hole. And within the ergosphere, nothing can remain stationary, not even light. But the ergosphere has a remarkable property. Unlike the event horizon, objects can enter the ergosphere and escape again. And by carefully navigating in and out of the ergosphere, by exploiting the rotational energy of the black hole, an object can extract energy from the black hole's rotation. This process, called the Penrose process, proposed by Roger Penrose in 1969, allows a black hole's rotational energy to be harvested. A sufficiently advanced civilization could, in principle, extract vast amounts of energy from a rotating black hole simply by dropping matter into the ergosphere and collecting the energy of the orbiting fragments. The spin of a black hole is not just a property, it is an energy reservoir, the most efficient energy source permitted by the laws of physics. We established earlier that the observable universe appears isotropic, the same in every direction, which implies it has no net rotation. But does it? This question is more subtle than it appears, and it is being actively investigated. In 2020, a team of physicists led by Leo Shamir at Kansas State University published a study analyzing the rotation directions of hundreds of thousands of spiral galaxies. They found a slight but statistically significant asymmetry. More galaxies appeared to rotate in one direction than the other. If confirmed, this would be extraordinary. It would suggest that the large-scale structure of the universe is not perfectly isotropic, that there is a preferred axis, a direction in the universe that is slightly different from all other directions, and that this preferred direction is reflected in the rotation of galaxies. A rotating universe, not rotating like a top, with a single axis and uniform rotation rate, but exhibiting a subtle statistical preference for rotation in one direction over another. This finding is controversial. Other analyses of galaxy rotation directions have found no such asymmetry. The debate is ongoing. The data are being scrutinized, but the possibility is real, and it has profound implications. A universe with a preferred rotation axis would break the Copernican principle, the assumption that there is no special location or direction in the universe. It would imply that the universe has a structure, an orientation, that we have not previously detected. It would change our picture of the Big Bang, of what preceded it, of what the universe fundamentally is. And it would mean that the question we started with, why does everything spin, has a deeper answer than we thought. Not just that angular momentum is conserved, not just that collapsing matter spins up, but that the universe itself, at the very largest scale, may be rotating, and everything within it inherits that rotation. Everything spins because the universe spins. We are not yet certain this is true, but the data are whispering something, and we are listening. Subscribe to Astrova for more videos that change how you see the universe. There is one more connection between spin and the deepest structure of reality that deserves attention: the connection between spin and time. We discussed the arrow of time in our 7 Things Before Time video. The fact that time has a direction, that entropy increases, that the past is different from the future, is one of the deepest asymmetries in physics, and spin, angular momentum, is intimately connected to another fundamental asymmetry. The weak nuclear force, the force responsible for radioactive decay, for the nuclear reactions in the Sun, violates a symmetry called parity. Parity is the symmetry between left and right. A universe that obeys parity symmetry would look the same in a mirror. The same physical processes would occur with the same probabilities, whether you are watching them directly or in a mirror reflection. The weak force does not obey this symmetry. The weak force has a handedness. It preferentially interacts with particles of one spin orientation over another. Left-handed particles, particles whose spin is aligned opposite to their direction of motion, interact with the weak force differently from right-handed particles. This violation of parity, discovered experimentally by Chien-Shiung Wu in 1956 and predicted theoretically by Tsung-Dao Li and Chen-Ning Yang, who won the Nobel Prize for the prediction, is one of the most fundamental asymmetries in nature. It means the universe is not perfectly symmetric between left and right. It has a handedness, and that handedness is expressed through spin, through the angular momentum of the particles that make up everything. The universe spins, and in spinning, it distinguishes left from right. The spin of particles is not just a property of matter, it is an expression of the deepest broken symmetry in the laws of physics. Everything in the universe is spinning. We started with that fact, and having followed the physics as far as it goes, through angular momentum conservation, through tidal torques and galaxy formation, through quantum spin and the Pauli exclusion principle, through pulsars and rotating black holes and the possible rotation of the universe itself, we arrive at an answer. Why does everything spin? Because angular momentum is conserved, and once introduced into a system, it never leaves. Because the universe began in a state that, whether perfectly isotropic or subtly rotating, contained within it the seeds of all the rotation we observe. Because collapsing matter spins up every time, at every scale, from the solar nebula to the stellar core to the galactic protocloud. Because tidal torques from neighboring structures transfer angular momentum into forming galaxies, twisting them into the beautiful spirals we see across the sky. Because quantum mechanics gives every fundamental particle an intrinsic spin, a rotation that is not rotation, an angular momentum that requires no motion. And perhaps, just perhaps, because the universe itself is rotating, slowly, subtly, in a way that is only now beginning to emerge in the statistical patterns of hundreds of thousands of galaxies. You are spinning right now, on a planet spinning at 1,670 kilometers per hour, orbiting a star at 107,000 kilometers per hour, orbiting the galactic center at 828,000 kilometers per hour, moving with the galaxy through the cosmic web at extraordinary speeds. And every atom in your body has electrons spinning around nuclei, and those electrons have their own intrinsic quantum spin, and the quarks inside the protons of those nuclei are spinning, all the way down. Spin is not something the universe does. Spin is something the universe is, from the largest scale we can observe to the smallest constituent of matter. Everything spinning.